Yeah, today we're going to talk more about doing hypothesis tests, but this time we're going to talk about hypothesis tests for means. So take a second and read this. This is from chapter 22, and we'll use this problem to talk about running a hypothesis test for mean. So we have a fleet of company cars, and it's required of them to meet the goal of 30.2 miles per gallon or better. And so this company takes a random sample of trips that their cars have gone on, and they find a mean of 32.12 miles per gallon with a standard deviation of 4.83 miles per gallon for those 50 randomly selected trips. So we're wondering if this is evidence to show that they've met their goal of being 30.2 or better. So we need to write hypotheses just like we did for proportions. This time we're trying to find about a population mean. And so we're going to use the Greek symbol mu to represent mean. And we're going to have an equals to here, so equal to that goal of 30.2. And we want to know if they're doing better, and so we'll have a greater than. We're going to test to see if we have evidence that they're doing better than that 30.2. We can't prove that it's exactly 30.2, but we can show that they're doing better, and that means that they'll meet the requirements. As always, we need to meet assumptions and conditions. These are the same as when we did a confidence interval. It needs to be a random sample, which in this case our trips were randomly sampled, the 50 of them. We need to have less than 10%. If this company is sending their vehicles on trips constantly, then we'll assume that 50 is less than 10% of all the trips that cars will take. And then we need our data to be nearly normal. So we don't know if that sample was normal, but we do have 50 trips sampled. So we have a significant sample size, so we can move forward. So we're going to do a one sample t-test for a mean, and we need to calculate a p-value. So our distribution of sample means is going to look like it did when we were talking about the distribution of sample means. We'll use our null hypothesis mean here for our mean, and then we need to calculate the standard deviation. So we're going to take our standard deviation from our sample and divide by the square root of our sample size of 50 trips. And so we'll get a normal curve that looks like this. Mean of 30.2, standard deviation of 0.6831. So we have to do something a little different here. We're going to calculate a t value. Remember, n minus 1 is degrees of freedom. We just take the sample size and subtract 1. X bar comes from our sample mean. This mean comes from our null hypothesis. And then that standard deviation we just calculated. So they did get a sample mean of 32.12 miles per gallon. Our 30.2 comes from the null hypothesis. And then that 0.6831 is what we calculated when we did the standard deviation above. And so we get a t value with 49 degrees of freedom of 2.81. And so that's very similar to a z value. It's a critical value. So when we draw our curve, we have 0 in the middle and 2.81 goes to the right. And so we're doing a one-tail, upper tail test. And so we're going to go on our calculator. So I'm going to go to my calculator, and much like we've been doing a lot this year, we're going to do second vars. And this time we're going to choose the T CDF because we have a critical value that's a T and not a Z. Enter our lower and upper just like we have been. So my lower is 2.81. My upper is 1e to the 99. And then I'm going to enter my degrees of freedom. So the reason we had to calculate this critical value is because you can see there's no place in there to put what the mean of our distribution is or what the standard deviation of our distribution is, because t distributions are different depending on the number of degrees of freedom. So it's important here that we've calculated a t value instead of just using our sample mean. So we're going to get a probability of 0.0035. And so here's our probability statement. Again, I'm writing t in my probability statement this time because that's what I'm using in this test. So the probability that we get a critical value with 49 degrees of freedom greater than 2.81 is 0.0035. So a very small probability. And just like when we were talking about proportions, what that means is that if the null hypothesis was actually true, remember when we're doing a hypothesis test, we're doing the test thinking or presuming that the null hypothesis is true. So if that is really the case, if the fumolage of this fleet is equal to 30.2, then we'd have less than a 1% chance of getting the sample results that we did. So there's a 1% probability that we get a sample of 50 vehicles, I should have said 50 trips, with an average fuel mileage of 32.12 if the true fuel mileage was 30.2. So that's almost impossible, close to zero. So we are going to reject the null hypothesis. We're going to use a significance level of 0.05 unless otherwise told, like we did with proportions. And since our p-value is smaller than that, we're rejecting the null hypothesis. And so we can say that with a p-value of 0.0035, significance level of 0.05, there is evidence to show that the fuel economy for their fleet is better than the required average. So they should be okay when it comes to meeting that requirement. So please make sure that you write down any questions so that when we talk about this in class, you can ask me those questions and I can help you through.